Hello, everyone. I'm Jingfan Meng from Georgia Tech. Today, I will present to you our ONIAC work. It's called One Index for All Kernels. This work is collaborated with Huayi Wang, Junxu, and Mitsunari Ogihara from University of Miami. We are working on a very extensively researched old problem. It is called approximate nearest neighbor search, or ANS. Let me briefly introduce this problem. We have a database D that consists of a lot of data points. These are black dots in this figure. And given a query object Q, it is a red dot. We want to find objects in the database that are closest to the query according to some distance metric. There are a lot of different solutions proposed for different metrics, such as Euclidean metrics, angular distance, Manhattan distance, and so on. In this work, we generalize this problem. And we generalize this problem to called ANS-ALT. It means after linear transformation. The query is not only a point Q, but also a linear transformation described by a matrix M. The goal is to find the data points that minimizes Mx minus Q L2 norm. So what does this mean? Different M's can change the matrix and determine different nearest neighbors. Such as in these two examples, suppose M1 stretches the horizontal dimension and compresses the vertical dimension, and M2 does the contrary. The nearest neighbors in these two different queries are different because in M1, the blue dot is closest to Q, but in M2, a different blue dot is closest to this query Q. So it has also a dual problem in which the database consists of pairs of matrices and vectors, and a query is a vector X, and we also want to find the pair that minimizes the same distance metric. We will see only ANS-ALT is very useful. It has a lot of vivid problems, and I will describe two of them in this presentation. The first one is called Mahalanobis search, ANSM. So what is Mahalanobis distance? It is, as you can see from this formula, it is a quadratic form of the difference between the query and the data, and given a kernel sigma, that is a positive definite matrix. We can transform this Mahalanobis distance into ALT form. So every Mahalanobis query can be reduced to a ALT query. And we can see a very recent work in 2020 has shown Mahalanobis search is useful in distance metric learning, but every existing work only works if the kernel is fixed for all queries or it's only changing slowly. If we have a solution for ALT, then we can naturally solve ANS Mahalanobis only using one index for all of the kernels. So this is a flowchart. In 2020, the solution only works it builds an index using some costly indexing procedures, but the index only works for some similar kernels. If the kernel changes beyond the capacity of this index, the capability of this index, then we need to re-index, and it is very costly. In this work, we can build an index for any kernel. So we pay this costly indexing procedure only once, and this index can be used for Mahalanobis queries for any kernel. Another useful problem of this ALT search is called subspace to point, or S2P, and point to subspace searching, P2S. These two problems are duals in the sense S2P, the data in the black ones are the points, and the query, the red one is subspace, drawn as a line in this figure. In P2S, the queries are a point, so these are duals, and the data in this database are subspaces. And we have shown the nearest neighbors in the blue color. We have shown in this paper that we can reduce the minimum distance variant and the minimum or maximum projection variance of these two S2P or P2S problems into ALT or HDU. So it is a very useful problem, and it can be used in computer vision like for 15 years ago. So now let's move on to the solution. The solution is when describing the solution, we only work on a simple formulation that we drop the query point Q, and we only want to like show how we solve this transformation matrix M. And we will show in this paper that these two matrices formulations are equivalent. So the idea is that we can convert ANS-ALT to ANS-L2 using a asymmetric mapping pair or AMP. So this is proposed in this work. And its AMP is actually like this. So given a data X, the mapping of this data called Fx is you first convert this, multiply this X is a column vector to its transpose, so get a D by D matrix. And then you flatten this matrix into a vector. The mapping of the query M is similar but different. You multiply M transpose by M, flatten it, and you add a minus sign to it. So this minus sign is crucial that it implies the following property, that the ALT distance, the L2 norm of MX is small if and only if the distance between these two mappings are small. So in this way, the ALT problem is reduced to the L2 norm searching problem under this mapping. We can build a conventional L2 index, for example, E2LSH. On the dataset, every point transformed by this mapping F. Given a query M, we also transform it to GM and search in the data using the E2LSH index, as shown in this figure. So this E2LSH index consists of multiple hash tables, and the datasets, the black dots, these are the data points. We first transform it with F. This is the AMP, and when we compute the hash values under E2LSH, this is under H. We insert it into this hash table. Given a query M, we first compute this AMP mapping GM, and then it's E2LSH hash value HGM, and get a bucket, and we retrieve every data item in this same bucket as the data. So it seems that we can that's all, but there's a caveat that the dimensionality of this Fx is D squared. If D is 1,000, then D squared is 1 million. So it can lead issues in the indexing cost and searching accuracy. So for example, we have computed that if the D and the number of data points are reasonably high, then the indexing can take years of time. So the solution, we also found that this issue has also arises in other different contexts. The standard mitigation technique is to sample only a percentage of the scalars, but it comes at a loss of accuracy. We propose a novel algorithm called fast GOE quadratic form that reduces its complexity to D log D from D squared. It means from years to days. How do we do this? The first step is we do some elementary equivalent transformation, and we reduce this hash value of this Fx into a quadratic form whose kernel is a Gaussian orthogonal ensemble. This is G plus G transform divided by 2. Our idea is to generate another kernel that has approximately the same distribution, but we can compute the value very fast. So the idea is that we can diagonalize a GOE using a random transformation. It's called a random transformation in the Haar measure. And we can replace this random rotation with a pseudo-random one, R prime. R prime, it has the formula as HD3, HD2, HD1. H is Hadamard matrix, and D, the three Ds are different instance realizations of diagonal matrices in which the values are random +1, -1 random variable. So we can, under this formulation, we can compute this HFX in d log d time, because it when you multiply with diagonals, it's OD. When you multiply with this Hadamard matrix, it only takes d log d time using fast Marsh Hadamard transform. So it has shown that this rotation matrix R prime is different, as there is a slight approximation error from a very uniform rotation, but this only leads to a very, very small negligible impact on the hashing accuracy. So the second solution proposed by us is GLT. It works if the D is very high in thousands. So this is a conventional dimensional reduction technique called Johnson-Lindenstrauss transform. So given this M, this is the query, we generate a Gaussian random matrix data and use this data M. So this is M after dimensional reduction in place of M. We have shown that this dimensional reduction is very effective, that the data points are most likely preserved. The nearest neighbors are most likely preserved, but it is also very much faster than to directly compute this MX. So now let's go to the results. So our first experiment is on the metric learning, Mahalanobis searching. We have 4 data sets of increasing dimension. One is the real one, and the 3 of one are synthetic high dimensional data sets. So we have evaluated ONIAC, so our LSH solution, JLT. Our second solution, LS is linear scan, and OASIS is the solution in this 2020 work. So we also combine OASIS with GLT as a study. So the result shows GLT outperforms the OASIS when the dimensionality is high, and the outperformance is like more than 1 order of magnitude if dimensionality is very high. We also try to evaluate on minimum distance like S2P queries. We use 4 real data sets of increasing dimension, and we evaluate GLT and ONIAC plus GLT with respect to linear scan. And we have shown that if the dimensionality is less than or equal to 128, then ONIAC plus GLT is the fastest. It is like 30 to 50% faster than GLT only. When the dimensionality is higher than GLT, is the fastest. So in conclusion, we have formulated ANS ALT and its dual. These are master problems to a wide range of ANS problems. We propose 2 solutions to ALT, ONIAC based on LSH, and GLT, dimensional reduction. These two solutions solve ALT and also solves these baby problems. We propose fast GeoEQF to solve the dimensional blow-up problem of this AMP and asymmetric mapping pair, and significantly reduces the indexing time of ONIAC. So thank you everyone for listening to this talk.